title of this presentation is On the Limits of Spreading Activation in ACT-R, Predictions and Testability. My name is Chris Fisher, and my co-authors are Brent Feegley, Christopher Stevens, and Christopher Myers. Cognitive architectures have several goals, including the development of unified theories of cognition and developing theories of cognition that scale to complex real-world scenarios. Part of this latter goal includes identifying memory processes and representations that support a large knowledge base. In this presentation, we address two related questions. First, what does ACT-R's spreading activation mechanism predict at fan sizes larger than those that have been used in the laboratory? In the laboratory, fan size is typically 1 to 4, but in some knowledge domains, fan size might be much larger. Our second question is whether there are practical limitations in the fan size that can be used to test spreading activation. In what follows, I will describe the famous fan experiment, the fan effect, and spreading activation as an explanation of the fan effect. The fan experiment is a paired associates recognition task. In the learning phase, participants learn person-place associations. Importantly, the number of associations a word has is varied. This is termed a fan size. In the example below, the fan size is 2 for hippie and 1 for the other words. The examples are, the hippie is in the park, the hippie is in the store, and the painter is in the house. In the test phase, participants indicate whether a given person-place pair was studied together. A target is a person-place pair that was studied together. An example of a target was the hippie in the park. A foil is a person-place pair that was not studied together, but the person and place were in the study list. An example of a foil was the painter in the store. The fan effect occurs when retrieval time increases with the number of associations a statement has. On average, we would expect retrieval time to be slower for statements about hippie compared to statements about the painter. The ACT-R cognitive architecture uses a memory mechanism called spreading activation to account for the fan effect. Each memory has an activation value which determines how quickly it can be retrieved. Activation spreads through an associative network and is divided across instances of a concept such as hippie. This results in lower activation and longer retrieval time as fan size increases. The mathematical details of spreading activation will be presented later. In our model analysis plan, we will develop a model hierarchy in which submodels differ in terms of activation noise. One submodel is the fan model presented in the ACT-R tutorial. We will analyze the model properties in terms of accuracy and reaction time. The general model in the hierarchy is called the guessing mixture model, which has a retrieval process and a guessing process. The GMM is illustrated as a multinomial processing tree on the right. Nodes represent states or processes, and branches represent transitions from one state to another. A path is a series of branches which terminates at a response node. The probability of taking a path is the product of transition probabilities along the path. A response probability is computed as the sum of path probabilities associated with a given response. Declarative memory consists of a set of chunks N. A chunk is a basic unit of declarative knowledge in ACT-R, consisting of a set of slot value pairs. An example of a chunk is person hippie, place park. We can treat a chunk as a function that returns a value given a slot. An example above, the slot person returns the value hippie. Because we are interested in fan size at large values, we assume Fan size f is the same for both person and place values. At minimum, the number of chunks must equal 2 times f squared. We need to multiply by 2 in order to create sufficient number of chunks for foils. The top right shows an example of one set of 4 chunks for a fan size of 2. The retrieval request is an equal probability mixture of retrieving from the person slot value and the place slot value. The parameter W is a mixture weight for the probability of retrieving from the person slot value. For simplicity, we set W to 1 because its value does not matter when F is the same for the person and place. Upon submitting the retrieval request to declarative memory, a set of matching chunks denoted R compete for retrieval. The chunk with the highest activation is retrieved if its activation is above the retrieval threshold tau. A person responds yes if the chunk matches the probe on both the person and place slot values. Otherwise, a person responds no. On target trials, one chunk in the set R matches both the person and place slot values, and F-1 chunks match only on the person slot value. Thus, increasing F will tend to increase misses through the sheer number of mismatching chunks. On foil trials, all F chunks match only on the person slot value, thereby leading to correct rejections when a chunk is retrieved. A retrieval failure occurs when the chunk with the highest activation is not above the retrieval threshold. In such cases, a guessing process ensues in which the model guesses yes with probability G. Each chunk is associated with an activation value that determines the speed and probability with which it is retrieved. Activation is interpreted as the log odds that a memory is needed. Activation consists of the base level constant, spreading activation, and normally distributed noise. Following other research, we allowed the retrieval threshold to be noisy also. There are two advantages of doing so. First, it produces graded changes and probabilities. Second, it allows us to analyze approximate equations for response probabilities. Spreading activation is defined below for a matching chunk and a partially matching chunk. The parameter gamma represents maximum association. The term 1/2 is the weight for sources of activation, which simplifies to 1 in the first equation. Spreading activation decreases with fan size F and can become negative. Although ACT-R software truncates spreading activation to 0 by default, we allow it to become negative because log odds range from negative infinity to positive infinity. We can analyze the limiting behavior of the model with a softmax approximation defined on the right for target trials. The first term is the probability of retrieving a matching chunk and responding yes, and the second term is the probability of guessing yes following a retrieval failure. As F increases, the probability of responding yes approaches G, the guessing parameter. This is because tau has the highest exponent, making the first term 0 and the second term 1 times G. The limiting behavior for FOIL trials follows a similar logic. The first term in the equation on the right is the probability of retrieving a non-matching chunk and responding no. The second term is the probability of guessing no following a retrieval failure. As F becomes arbitrarily large, the probability of responding no on a target trial is 1 minus G. In what follows, we will examine the behavior of the model for two special cases, Tm, which is the tutorial model, and Tm plus n, which is the tutorial model with noise. The parameters used in the simulations are shown to the right. In the tutorial, activation in the Tm was always above threshold because fan size was small. At larger fan sizes in our simulations, we assume that an unbiased guessing process occurs after a retrieval failure. As a result, accuracy is a step function for target and foil trials. Accuracy is 1 and drops to zero point 0.5 as soon as activation drops below the retrieval threshold. As shown on the right, reaction time increases with fan size and flattens following the switch to pure guessing. The deterministic behavior of the TM is not plausible. For this reason, we extend the TM by adding noise to the activation and retrieval threshold to allow graded changes in the response probabilities and reaction times. Fan size was varied up to 250. The retrieval threshold tau was 0 or 2. The maximum association parameter gamma varied from 1 to 4. We repeated each condition 5,000 times. Accuracy for target and foil trials are found in the top and bottom panels respectively. Lines for gamma are color-coded. Tau is solid at 0 and dashed at 2. Here are some notable patterns. Overall accuracy decreases as a function of fan size and eventually converges to guessing at 0.5. On target trials, accuracy often decreases below 0.5 before reversing trend and asymptoting at guessing. The rate of decrease depends on the difference between gamma and tau. A larger difference corresponds to a slower rate of decrease. In the grid plot below, rows correspond to correct and incorrect reaction times for target and foil trials. Columns correspond to different values of tau. Gamma is represented as color-coded lines. Overall, reaction times are within plausible ranges despite low activation values at high fan size. As expected, reaction time gradually increases with fan size. Reaction time decreases with increases in gamma and tau. Lastly, we note some practical challenges with testing spreading activation at scale. The main problem is that time complexity of the fan experiment is OF squared. As shown in the figure, the time required for the study phase quickly becomes intractable. In most experiments, the time required will be much larger because multiple fan sizes are used. As shown on the right, the time between repeated presentations of the same pair increases with fan size. During the intervening time, memory will decay. More time will be needed to counteract decay with additional practice. One of the most interesting findings was that accuracy was relatively low under a wide variety of conditions. Experiments are needed to test these predictions. However, one practical challenge is the nonlinear increase in time demands as fan size increases. Nonetheless, we believe that testing spreading activation at scale is integral to the development of unified theories of cognition. Thank you for your interest in our presentation.